if you can make this part, you can make any of these ribs. Took this example and reverse engineered this and came up with this thermoplastic design.
And what resin is in there?
It's a low melt PAEK resin.
LMPAEK.
This continuous fiber low melt PAEK piece was fused to this one through a PEEK interface.
You had to do this after overmolding, right? You added this after?
No, they all happen at the same time.
In this part 2 video, you're in for a treat. The director of NIAR shows us a thermoplastic composite part which is overmolded in one shot. It is one of the most complex parts I've ever seen. And it is a wing rib for an electric aircraft. Check it out.
So I'm with NIAR, or National Institute for Aviation Research at Wichita State University. I'm the director of NIAR Atlas. Atlas stands for Advanced Technologies Lab for Aerospace Systems.
Okay.
And it's set up to create a maker space in the United States for advanced manufacturing. Our partner Joby, when they came and say, hey, you know, we like what you did with the window plug, but we want to challenge you because if you can make this part, using your technology, you can make any of these ribs in a typical eVTOL structure.
Wing ribs are structural components inside of an aircraft wing. You can think of it as the skeleton of a wing, where it provides mechanical and structural stability to the outer skins of an aircraft wing. Historically, these have been machined from very large metal billets, but as you will see very shortly, this is also very suited to be made out of thermoplastic composites in a much more efficient way.
This part we're looking at a rib of a V-tail, right? Where you have the V-tail here, the top skin, bottom skin, that's the front spar attachment, that's the rear spar attachment. This is where the engine attaches at the V-tail. But this is a very intricately machined part that probably take, 80 some hours to machine, right?
Giant
and then you probably have to machine like 80% of it. So we take these examples and reverse engineered this and came up with this thermoplastic design. And basically, you can't take this exact same part and convert it to thermoplastic because you have to redesign the part to meet the requirements, right? So you can see this is a C channel, but in a thermoforming, you can't pull a C channel out. So we had to make a Z, right? And then we've done several redesigning. So before we do the manufacturing, we do the thermoforming and overmolding simulations, injection molding simulations, during the designing, in order to design the tool very effectively. These are very, very expensive tools, so you can't do trial and error. You got to get it very close to near perfection, right? So we do a lot of simulation prior to spending money on the tools. So the way it works, you start with this flat continuous fiber sheet. So this has continuous fiber, whatever the layup you want. So it looks like a piranha.
And what resin is in there?
This is the Victrex AE250. It's a low melt PAEK resin.
LMPAEK, that is getting a lot of use lately.
So because it's aerospace qualified material.
It is qualified
right?
now.
So because in aerospace, that's an important step to have a qualified material to demonstrate the repeatability and reliability of your material, right?
If you're wondering about LMPAEK, let me give you some headlines. If you're curious about the world of thermoplastic composites and the different types of thermoplastic, you can go check out my video exactly on this subject. But for the headlines, really, you have, among all the different types of thermoplastics, you put it in a pyramid. At the tip, the apex of the pyramid, you have PEEK material. And PEEK material is an incredibly high-performing material. Now, LMPAEK is actually very similar to PEEK. It has got the same chemical resistance, the same thermal stability, and pretty much it is the kind of material which has got the same mechanical properties. The one difference that LMPAEK has got is it has got lower melting point, and this opens a few opportunities. This allows for shorter cycle time. So when you need to heat up the material, you're heating up the material to a lower temperature, and then you're cooling it from a much lower temperature. So cycle time happens a lot faster compared to PEEK, where you have to put a lot more energy and a lot more time in processing this material. And also LMPAEK is easier to weld in terms of there's a lot less thermal stresses happening. The next one is this material has got great flow characteristics, so the consolidation of it is much easier. You can do things like in situ consolidation, which is one of the holy grails of the automotive and aerospace industry, and you can get pretty low void content. It is also easier to give LMPAEK better impact performance. If you have cooling control in your manufacturing process, you can control the crystallinity of this material and therefore control the impact performance of this material.
So basically you start with the continuous fiber low melt PAEK, this organo sheet, right?
Yeah.
It's already compressed, all the air bubbles, everything's taken out, and you trim it for making it. So you put your organo sheets on one side, and then the first step you actually thermoforming. So you can see the thermoforming in all kinds of different directions.
It's been stamped in a lot of directions.
Yeah, exactly. Yeah. The second step, multiple things happen. Now, when I say second step, these two steps happen back to back. So it's not a two-step process, it's a single-step process.
So you form it and overmold it on the same tool for
same tool at the same time.
I thought it was two process. Look at the complexity.
Because if you were to do a two process, you actually introduce a lot of internal thermal residual stresses. Actually, you end up failing the part. So as soon as you form this, the next step is to inject this resin. This is a PEEK material with a 40% chopped fiber. It does three things. First, it basically fills up this cavity where we have to attach the engine. And also it fills these edges so you don't have to do secondary machining.
Yeah.
So it's a net shape part.
That's really nice.
And also we have continuous fiber gussets to counteract some of the bending loads. And this continuous fiber low melt PAEK piece was fused to this one through a PEEK interface.
But you had to do this after overmolding, right? You added this after?
No, they all happen at the same time.
So in your mold tool, you had this in there?
So you can see on this, the robot goes in and pull the finished part. At the same time, on the other side of the robot, we have these three gussets. And then the robot actually insert them into the mold.
Oh, wow, that's really clever. That is awesome. You've done all of that in
one step, yes.
That's awesome.
And here you see the process for making it. So you put your organo sheets on one side, you put your gussets on the other side.
Yeah, that is.
Robot picks it up, take the organo sheet into an oven. So you get make it the material soft formable.
Yep.
And then you drop it into the tool.
And who makes your machine?
So this is the Kraus Maffei dual injection machine. It's a German company. So here's the three gussets it's picking up.
I can see.
And in the first it goes and pick up the finished part, and on the other side it's insert the gussets in.
Very nice.
So it's a fully automated process. One side you put in the organo sheet, and on the other side you actually have the finished part.
That's very nicely executed. Okay.
Right now what we do is we make the organo sheet somewhere else. We send it to a machine, chop, trim it, and all of that, multiple location. We are working with Phil right now, adding more equipment into the mix, where one side you basically load the material and it does a near net shape layup with ultrasonic welding, all the plies.
Okay.
And then consolidate it, trim it. With this setup, one side literally you loading the thermoplastic material on the fill multi-layer machine. And then it goes into the consolidation cell to make sure they are nice and compact. The next cell, it does all the drill trimming and make this, piranha looking part. And then from there it feeds directly into the machine.
And you can have then a custom-made laminate with exactly what you need and really reduce waste, right? Because
it's a net shape layup and things like that. Because like when we do this, like in these parts, we have a flat laminate, so all these cutouts. I mean, here the wastage is very minimal, but we can minimize the wastage even further by doing the near net shape layup and then doing the trimming. So this is one of the most complicated ribs. Obviously, we demonstrate the manufacturability. Now we need to make sure we need to demonstrate the certifiability, because if you cannot certify...
But that's a challenge. The big question is, that joint, does that last 20 years or whatever it needs to be?
So
it's a big challenge.
During certification, we minimum test an article for 2 lifetime. But the window plug, we actually did 3 lifetime with damages in it, but still couldn't fail.
That is amazing. Thank you
very much.
Yeah,
nice
it's
meeting you.
An absolute pleasure. Thank you so much.
This is the cutting edge when it comes to thermoplastic composites. If you like what you saw, do click the subscribe button. It really helps to grow the channel, and I will be bringing you a lot more in the near future. In the meantime, I will see you soon. Peace.